Hi, today we're going to talk about exponential functions. These are the type of functions that are used a lot in the sciences. Now, before we get started, you need to get a good scientific calculator. Now, the one we recommend in our department is the TI 30X2S, and I've been using it all semester in the course. To evaluate a function using this calculator with exponents, you will need to use a key that looks like this. It just has the little up arrow or the little uptick. Let me make that a little bit neater. There we go, like an upside down V. Some calculators, the exponent key will look differently. You will also need to remember how to round off a decimal number. Many of your answers will be decimals. We're going to round these two numbers to the nearest hundredth. The hundredth is the second decimal place behind, and you notice this 7 is in the place, but next to it is a 1. The way the rounding rule goes, if your number, the third number behind the decimal, is 4 or lower, then you would just drop that off. So my answer rounded to the nearest hundredth is 5.67. Now in the next example, I have 5.67522. The rounding rule says if the third decimal place, the place past what you need, is 5 or larger, you have to round up. So my answer rounded here will be 5.68. So just remember the rounding rules. Now let's go and try some calculator problems. Get out your scientific calculator and go ahead and calculate 5 raised to the exponent 2.2. I get 34.4932415. Now I need to round this to the nearest hundredth, so I go 2 places behind the decimal and there's a 3, so I drop that off. So my answer is 34 and 49 hundredths. Now let's go ahead and try the next example. 2 raised to the exponent of negative 6.9. This time I get the answer of 0.0083733. I want to round that to the nearest hundredth, and I notice in the third decimal place there's an 8, so I need to round up. So my 0.00 goes up to 0.01, rounds up. Now, just to show you the keystrokes on my TI calculator, on the first example, I had pressed the 5, and then the exponent key, and then 2.2, and the equal sign. When I did my second example, I pressed the 2, then the exponent key, then I pressed a key that has the negative sign, and I press 6.9, then the equals. Now, in addition to using your calculator, we're now going to cover a special number called Euler's number. This deals with the letter E. Whenever you see this letter E in upper level mathematics, that is known as Euler's number. Now I know it looks like Euler's, but it's really Euler's. Euler's number is a little bit like pi, the 3.14 number. Euler's number is irrational, like pi, and it is approximately equal to 2.718. Now, Euler's number is what we call the constant of continuous and natural change. Euler's number is used when studying population growth or how quickly a virus may spread. You'll see here that the number is used in real-life problems. Now, when you need to use Euler's number on my brand of calculator, the TI-30X2S, you will need to press two keys. For my brand of calculator, I have to first press the second key, which is like a shift key in the upper left corner, and then I have to press a key that has a capital L and a capital N, because right above that, I have the little bitty e to the x. Now, let me try this with the calculator. So using my calculator, I will press second function ln, and automatically e to the x pops up. Okay, now I'm going to press my negative 0.91. So here's what I have typed into my calculator. I'll just hit equals, and I end up with 0.4025, and it goes on, but I just need to go to the nearest hundredth, and I notice a 2 is in the third place, so I can drop that off. So it's 0.40. Be careful when you're rounding this off. Now let's go on to the second objective. The second objective is to graph exponential functions. Right? An exponential function has the x value. Notice it's right here. The x value is the exponent. So when you substitute in a number for x, you'll be substituting in for the exponent. The first thing we'll do is fill in the chart with the graphing numbers. I will use these numbers one by one. So first, I will have 3 with the exponent -2. If you've studied negative exponents before, you know that that just means to flip the base, which means take the reciprocal and flip it upside down. And 1/3 squared is 1/9. So that's the answer for the first function value. Now let's do the second function value. If I have 3 to the -1, again, negative exponent means to flip the base. That would be 1/3 to the +1, which would give us 1/3. When I use the 0, 3 to the 0 exponent, if you recall your exponent rules, 3 to the 0 is always equal to 1. Now feel free to use your calculator on any of these values as well. The next one would be 3 to the first. 3 to the first is just +3. And then lastly, 3 to the second would be 9. So those are my values. When I graph those values, I'll go -2 and then 1/9, which is barely a little blip on the screen there. Then I have -1 and 1/3. Again, barely a little blip on the screen. Then I have 0, 1. So I go 0 and then up 1. So there's a point. Then I have x is 1, y is 3. So I go to my x is 1 and then I count up to 3. Then I have x is 2 and y is 9. Now that's actually off the screen, so let me just try to make some more tick marks. So 2 goes all the way up to 9. And when I connect the dots, you will see a curve. And this curve is very typical of how natural and constant or any type of exponential change happens. Another very practical use of exponential functions is compound interest. Anytime you go to borrow money or hopefully even invest your own money to make more, compound interest is used. This is the formula that we use for regular compound interest. The values there for each of those letters would be A is the accumulated amount. I'll just abbreviate that. P is the principal. Now, if you need to write this beside principal, principal is the amount of money you start with. R is the interest rate. and that will need to be written as a decimal, not as a percentage. N stands for the number of compoundings per year. So that's the number of compoundings per year. And then T is going to be the time, and that will always be given in years. Now, when it comes to compounding period, here are some of the most common ones. You will hear the word like annual or APR, annual percentage rate. Annual means once a year, so you will let N equal 1. Next, you will hear semi-annual or biannual. That means your interest is compounded twice a year. Quarterly. There are 4 quarters in a dollar, and there are 4 quarters in a calendar year, so N equals 4. Monthly compounded interest means you compound it 12 times a year, and daily compounded interest, which is the same type of interest most credit cards use, is 365 times a year. The more you compound your money more often per year, the more interest is earned. Or if you're borrowing money, that's the more interest you owe. A second type of compounded interest is called continuous compound interest. You don't see this very often, but we are going to cover it. Here is our formula, much shorter formula than the other, and it uses Euler's number. The A is still the accumulated amount, the P is still the principal, the R is still the rate as a decimal, and the T is still the time in years. Now the E here, remember, is Euler's number. So that is actually programmed into your calculator, as we had seen earlier. Now let's go through some examples. We want to find the accumulated value of an investment. So we're looking for the A. The investment is $15,000. That's our P. That's what we start with, the principal. It's 4 years, so that's our time, our years. The interest rate is 5.5%. You need to move that decimal point over 2 places and let R equal 0.055, just like that. Now, if we want to compound this semi-annually, N is equal to 2, quarterly, N is equal to 4, and monthly, N is equal to 12. Now let's go ahead and substitute this into our formula. It will first be A equals the principal, 15,000, times 1 plus the rate, 0.055, divided by the number of compoundings, and then as an exponent you will have the number of compoundings times the number of years. Now I put that in parentheses up here. What some people would do is just go ahead and call that 8. So you could type it in your calculator as 15,000 times 1 plus 0.055 over 2 raised to the 8th exponent. Now I'm going to type that in my calculator using those same parentheses. So 15,000 parentheses 1 plus 0.055 divided by 2 will make me have a fraction, close parentheses, exponent, and 8. And that will give me the answer of 18,635 and 71 cents. So my $18,000 raised $635.71 in interest. Now let's do the next problem. It's quarterly. It will be set up the same way, except the compounding period would be 4 for quarterly. So everywhere I had a 2 before, I will now put a 4. That means that this exponent is actually going to be 16. So I will put that in, 15,000, open parentheses, 1 plus decimal 0.55, divided by, gives me the fraction bar, 4, close parentheses, exponent 16, equals. This time I get $18,663.16. Notice that it's a little bit more interest that's earned than before. Remember, the more often you compound your interest, the more interest is made. Now for monthly. A equals 15,000 times 1 plus 0.055 divided by 12. Everywhere there was a 2 or a 4, I now put a 12. That's going to be 12 times 4. That exponent then is going to actually be 48. Let me type that in, 15,000, parentheses, 1 plus decimal 0.55 divided by 12 is my fraction bar, close parentheses, exponent key, 48. And that will give me $18,681.76, a little bit more. Now, let's do one more part. Let's compound it continuously. Use the other formula for compounding continuously. So I will have A equals 15,000 times the E. Now the exponent this time is decimal 0.55 times the 4 years. Notice you don't have the letter N in this formula. So I'll type that in my calculator, 15,000. Now on my TI calculator, I have to hit the second function, and then I have to hit the LN key to actually get that to come up on the screen. So 0.055 times 4, and I will get $18,691.15. So continuously gives you the most interest, but we don't normally see that type of interest at banks anymore. Hope this gives you an idea of exponential functions.